The goal of this exercise is to compute a probability ratio for the Planck spectrum. So imagine that we have some object that produces thermal radiation, meaning that its distribution function is described by this. So it's a function of energy and temperature. Graphically, looks something like this. So this is the Planck distribution function as a function of photon energy on the x-axis. The most probable energy, of course, ends up being at the peak of the spectrum. The average energy, E bar, is somewhere to its right, and I didn't worry too much about drawing that very accurately, but conceptually, that's the relative positioning of the two energies. What we want to know is what is the ratio of probability of finding an energy at the peak compared to the probability of finding E bar. So we can construct that probability ratio in much the same way that we did for the Maxwell-Boltzmann distribution. So we'll start by writing that each probability is approximately equal to the distribution function times some delta E, where delta E is assumed to be small. Remember, this is how we turned the differential element in an integral into a difference where we didn't have to integrate. Well, in this case, we're taking a ratio, though, so each of those delta E's is just going to cancel with the other. That means that the probability ratio is just the ratio of the distribution functions. So now we can enter in the specific form of the distribution function, making sure to evaluate the one in the numerator at EP and the one in the denominator at E bar. So we do that, and we can see that we're going to cancel out some constants, so ultimately this ratio gives us EP over E bar quantity cubed times some exponentials. You have to be careful to make sure that you track your bars and subscripts correctly. Having the nested fractions with exponentials can be a little involved, but we did it right. So we'll save this, and now we can evaluate this. We know the ratio EP to E bar. It may not be obvious. Unlike the Maxwell-Boltzmann distribution, where you could actually figure out the average speed or the most probable single speed, for the Planck distribution, it's quite challenging. Trust me on that. I won't make you do it. But fortunately, your lecture notes provide expressions, so the average energy E bar is equal to 3.83 kT, and E sub p is equal to 2.82 kT. That's nice for a couple of reasons. One is that tells us if we want the ratio of EP to E bar, we have to take the ratio 2.82 to 3.83. That's where I get this 0.7363. It also tells us that since the quantities and the exponentials are in terms of kT, hey, they're also getting divided by kT. That's great. So we actually don't need to know the temperature of the system to do this calculation. All the t's factor out. So now we can simplify this and reduce some of the math to see that the probability of getting the most probable energy compared to the probability of getting the average energy is 1.14. So the most probable energy is 14% more probable than the average energy for the Planck spectrum.